Hello everyone and welcome back to another video. Today we'll be taking a look at another British Informatics Olympiad question taken from the 2011 paper, and we'll be taking a look at the second question. So I'll let you have a quick read of the question before I explain what I understand from the question as well as my solution to this question. On the screen you'll notice that I've basically highlighted the important parts of the question. Pay attention to these parts, and yeah. That's pretty much it, okay? So, and now I'll go and explain my solution on the whiteboard. So, how this works is that there are three different strategies which we have to use for basically combining the deck, right? But first we need to actually lay out all the cards inside the deck. So for this we would need to create some sort of shuffle function. So what this does is that this would basically take an original set of cards, which are all in a predetermined order, and then make them into a new set of shuffled cards. And that will be our first function which we need to have. This function will be applied before any of the other ones are applied. And now the second function which is essential is a function which determines whether certain moves are valid or not. And now, if you remember from the question, we basically have some sort of condition for validity, and it's in the third paragraph if you want to quickly refresh yourselves on it. But how it is it checks whether the first character or the second character is the same of two cards. And now these two cards can't be any two cards. They have to either be one apart or three apart. So we need to determine some sort of valid function which returns all possible valid neighbors of the card which can be combined too. And then the third major part of this code will be the three different strategies which we will use for actually combining the different cards. And now I'll write it down here, and then for explaining what these things do, it's probably easy if I just go straight to the code. So I guess let's have a look at the code now. Okay, so I'll walk from it line by line from the start. So we import the deck data structure. Now the reason why we use this will become very apparent later on, but essentially in a nutshell it's because the deck structure has several more favorable properties compared to a list, since it can be used to perform operations such as rotate, rotate left, pop left, all of which are not available in the list, which will become very useful in this question. Okay, so we initially start with some sort of predetermined order. This order is for the shuffling order, which is as an input to our class game. And then we have our initial arrangement of cards. Now, don't worry, I did not just like hand type all of these 52 elements. In another window, I basically created some sort of two for loops just to generate this initial array element. The reason why is just because it's going to be like that every time, so I might as well just hard code it in. And okay, so now we have self.table. Now this self.table will basically contain all the different piles, and we also have the stack. Now this stack determines the length or the height, if you like, of each of these piles. And now one thing which you might notice in the cards is that I am keeping everything as a string, but one very important thing is that I'm only keeping the top element as the cards for a particular index inside the tail array. Now the reason for this is because we don't need to store all the card values below the top element. We only care about the top element, right? Since we only use the top element when combining and stuff. So that will save us significant amounts of memory space if we only keep the top element, but then at the same time we don't want to lose data of how tall the actual pile is. So we also keep data of the actual pile length as well as the top element only. Now we have the merge function. Now this merge function is a relatively unimportant function, but it basically just merges two elements. I think the code's pretty self-explanatory. What we do is we pop a certain index value, the second index value, and then we also pop the size value. then we add the size value onto the first index value, which we want to append the card to. And then the first index value, we also make the top value of the second pile the one of the first pile. Since remember, two piles are merged, the second pile goes on top of the first pile. Okay. Okay, and now now let's look at the shuffle function. Now, what this function does is pretty much exactly how I explained on the whiteboard. It shuffles the cards. So now the cards is a deck, and now what we do is, while true, so this will just repeat indefinitely, we iterate through each element inside the order, and now we have a second iteration which iterates till we get to the element -1. Since if you remember in the question, it basically said that until we reach the 8th card number inside the pile, we should continue placing that card to the end. So then, since in the question they used one base indexing, since they were first, second, third, but then obviously in computers we use zero base indexing, which explains why this is L-1. Okay, and now we basically have this, and what we do is once the length of the cards is 0, then we return, if that's the case, since we have no more cards to shuffle. Otherwise, we perform this rotate function. Now, this is where the double-end queue or deck actually comes in handy, one of the places where it comes in handy, since what rotate and with the -1 parameter does pass to it is it literally rotates it left, which is exactly what we want. So, and how do we, if we were to do rotate 1, then it would rotate right, basically. So bear in mind this function, it will come in useful in this question and several others down the line. And now this line is pretty much similar significance to this line. It's just that if we reach the end, then we basically just return. And then finally we append, we basically append whatever the final element inside, whatever the first element, sorry, inside our table is to like the, sorry, whatever the first element inside our cards array is to our table. And then we just repeat this 52 times for each of the cards. Okay, and now now let's have a look at the valid function. So this valid function again does exactly what it says on the tin. We basically just take a certain index, then we look at its adjacent one and the one which is true left to it, and we basically append them to an array. And then what we do is we use this list comprehension to determine which elements inside the array are valid. And now what we do is L for L and R, so we iterate through each element in an array. And if the elements, if the first position in the element aligns with the first position in our C1, C1 is the card 1, it's the current card which we are comparing with, or the second element aligns with the second element in C1, then that particular element will make a place inside this valid array. And then we repeat this for both of the other elements. Then we return the valid array. And now I'll come back to what this all valid function does, since this will be useful in the code for the strategy 3. But before that, we need to look at strategy 1 and strategy 2. So if you recall, strategy 1 was basically just we combine from the right, and then whichever the first element from the right which can be combined is, we should combine that, and selecting adjacent ones if possible. And now, if you notice that in all three of the strategies, they prefer adjacent ones to the one which is to left, which is why inside our valid function, we went over the one which is left first, and then we went over the one which is 2 to the left after that. So now, anyways, back to the strategy 1, we iterate backwards, so from the penultimate, from basically the final index, since remember we start with 0 based, going to -1 because range is exclusive, and then going in steps to -1. And then we basically just create some sort of array which is the valid elements around a certain index value. And then if the length of the array is greater than 0, i.e. if there is some sort of valid neighbor which the particular index value can be swapped with, we basically just favor to return that particular index and its neighbor. Since remember what the strategy function does is it returns the two neighbors or the two indexes which need to be merged. So we basically just iterate through this until we find a neighbor which is valid, and then at that point we just instantly return that, and then we're finished. And now if we get to the case when we iterate through each and every element and we don't find any such valid pair, and we return 0, 0. This will be our kind of like exit case, if you like, since there's no more valid moves which can be performed. So that's strategy 1. Now let's take a look at strategy 2. So strategy 2 basically creates the largest pile possible. So again, we iterate backwards since the elements which are right have a preference, and then again, elements which are adjacent also have a preference. And then we also create this one more size variable. Now this has the size of, this basically stores the size of the current merge pair which we have. So initially the merge pair will be of length whatever the initial particular index value is, but then it will also be incremented by the neighbor which we will combine with the index value. And now if that particular size value is greater than the best option, and now this best option array basically stores, it has 3 elements inside it. Its first element is the maximum size length, which we currently have, and the second and third element are the 2 index values which that size length was attained by. Now this is all vital information since we'll be returning the 2 index values, and then the first value, which is the length of the maximum combining array, we'll be using that to compare with different pairs, and then whichever one's the greatest, like in this case, if it enters this if loop, then that particular combination will be the greatest value possible so far. So then the new best option will be size, which is the current size, and ind neighbor. Okay, and then we basically just have to reset the value of the size variable to whatever it used to be. And now we just repeat this for each of the elements inside the array, and then finally we return the 2 indexes of the best 2 values. Okay, now that's strategy 2, and now let's have a look at strategy 3. We use a similar code to last time. We have some sort of best option. In this case, the first element isn't the largest possible array, but it's the longest possible number of moves which can be performed. So we again iterate backwards, and the code's pretty much identical with one small change. Notice in this code how we generated the size value was we basically added the initial index value as well as the value of the neighbor. But in this one, we need to look at the all-valid function. And now let's have a quick look at the all-valid function. So what this does basically is it creates, it kind of goes, it looks into the future, if you like, because it looks at each possible move, and then it looks at how many moves are possible if we go down that move. Okay, so the reason why we pass the 2 indices to it is because what the all-valid function does is it performs the merge of those 2 indices, and then of the resulting array, it sees how many possible moves there are. So we basically we create a deep copy of the table and the stack, and the reason for this is so we don't lose the data which is inside the table and stack. And now what we do is we basically just, these 4 lines perform the merge, basically, inside the 2 indices, except we basically, and then after we perform the merge, we iterate through each element inside the new table, and then we see how many possible valid moves there are. And the way we do this is we increment it by the length of the valid array. Okay, and we do this for each of the elements inside, and then that will give us an idea of how many possible moves which can be done with our new array. And then don't forget, at the very end, we need to recreate the copies of the table and stack, since these two variables are temporary, and then we just reinstantiate the values inside. So that's basically the strat3 function, since apart from this all valid function, everything else is identical to strat2. And then we return the best option. And now let's go to the play function. This play function puts everything together. So what we do is we have the three functions, strat1, strat2, strat3. And then while the length of the table is greater than or equal to 1, we perform the particular function. The particular function will return the two indices which we need to merge. If both of them are 0, then remember that's our invalid case, so then we break. Otherwise, we perform the merge. And then we repeat this until either it's of length either it's of length 1, or both of them have been both of them are 0, so that's our breaking condition. So that's basically it. And then this piece of code is fairly trivial. We basically just iterate through the play function 3 times, each time passing a different function or a different strategy to be played. Okay, so that's basically it. Now let's see if our code does actually work. Let's go back to some of the test data given in the question. Okay, so this was our output from the program. And this is indeed correct. Maybe let's test it on one of the other ones from the mark scheme as well. Let's test it on maybe this one. Okay. Now let's go back and execute this. And then if we go back to the question, we can indeed see that this one is correct. So our code does actually work. So that will basically be it for today's video. I really hope you enjoyed this video, and hopefully you learned something new. Maybe it was about the deck structure, maybe it was about how we modularized our code and made it quite easy to understand as well as easy to implement. And yeah, I wish you luck in your competitive programming journey. If you found this video helpful, please be sure to leave a like. Do check out my GitHub as well if you would like to have a more in-depth look at the code and play around with it a bit more. And I hope to see you in another video next time. Thank you very much for watching. Bye.